Hello, everyone. My name is Stephen Hernandez. I'm a PhD student in the Department of Computer Science at Virginia Commonwealth University. Today, I will be presenting our work on using Wi-Fi sensing to detect soil characteristics. Projections suggest that by 2050, agricultural food production will need to increase by 70% to keep up with global population growth. Precision agriculture is one important way that we can achieve this need. Specifically, precision agriculture uses sensor data to give farmers better insight into their land usage. This ensures that farmers can reduce the amount of wasted resources as well as increase their yield. Our goal is to demonstrate the use of Wi-Fi sensing to sense the following soil properties: moisture level, soil texture, as well as sensor position, such as the depth and distance. Why do we want to use Wi-Fi? In some of our previous work, we've demonstrated that it is possible to use low-cost microcontrollers, such as the ESP32, to perform Wi-Fi sensing. Additionally, Wi-Fi-based systems allow us to not only perform mesh sensing, but also mesh communication. How does this proposed system work? A set of ESP32 microcontrollers are placed directly in the soil. Each ESP32 can act as both transmitter and receiver within the mesh network. The signals propagating through the soil from transmitter to receiver is directly affected by the permittivity and conductivity of the soil. As such, each ESP32 captures some characteristics for these received signals in the form of raw CSI. By capturing this raw CSI, we can perform pre-processing and run machine learning models directly on the ESP32. Now let's look at some interesting results from our work. For the first experiment results, we look at how well our system can detect both soil texture and sensor depth. The transmitter and receiver are placed into the sand and silt soils at three depths: 10 centimeters, 20 centimeters, and 30 centimeter depths. From the confusion matrix, we can see that our model is able to accurately predict both the soil texture and soil depth at greater than 98%. This result shows that the model can achieve a depth resolution on the order of 10 centimeters. Additionally, it shows that sandy soils have unique characteristics from silty soils, which can be leveraged to better calibrate our system in new environments. Next, we look at our Wi-Fi sensing system's ability to recognize soil moisture levels. For this, we start out with 1,200 milliliters of dry soil, which we then mix some number of milliliters of water. In the confusion matrix shown, we mix in 60 milliliter increments of water into the soil. From this, our prediction model can achieve accuracies of greater than 92% for all classes and 98% for most moisture level classes. Now that we've reviewed some results from our lab environment, we want to better understand how will Wi-Fi signals actually propagate in physical environments. To review this, we place our transmitter and receiver in a real field in both overground and underground conditions. In the two line plots, the x-axis shows the distance between the transmitter and receiver. The y-axis for the left figure shows the number of Wi-Fi frames received per second, while the second figure shows the average RSSI at each distance. The transmitter sends at a rate of 100 frames per second, and as such, the receiver in the overground experiment is able to receive at a constant rate of 100 frames per second. In the underground experiment, however, we see that the receiver is not able to receive any frames when the devices are placed at greater than 6-meter distances. In the right figure, we can see that the RSSI values decrease for both overground and underground scenarios. When the distance is greater than or equal to 6 meters, the RSSI for the underground scenario will have reached below the noise floor of -90 dBm. Thus, we do not receive any frames of data. With these maximum distances in mind, we next look at some simulation experiments. In these simulations, we want to identify the amount of coverage that our sensors can achieve for measuring soil moisture properties. As we showed in the previous slide, as long as two nodes are within communication range, the signal is able to travel through the soil, and thus we were able to measure soil moisture between those two nodes. 16 nodes are placed in a grid such that the neighboring nodes can communicate with one another. The red indicates the area where Wi-Fi signals propagate and thus where sensing can occur. If we decrease the grid spacing slightly, then we can actually increase the number of connections, and thus the coverage also increases because the diagonal neighbors can now perform communication. However, if we decrease the grid spacing too much, we only have coverage in a small localized area. We simulate this grid with different distances from 0 to 6 meters. We can see in the first figure, when the distance is very small, the devices are essentially placed on top of one another. Thus, the number of connections is maximized because all nodes can communicate with one another. However, the coverage is minimized because each of these connections is overlapping one another, resulting in redundant sensor data. We find that increasing the grid distance up to 3.8 meters decreases the number of connections by half, but increases coverage to a maximum value of 25.3% coverage. Because our proposed Wi-Fi sensing system is able to leverage multiple connections for performing sensing, we're able to achieve much higher coverage compared to standard sensor-based systems, which can only sense in a small, localized area. As such, we can see that our proposed Wi-Fi sensing achieves a maximum of 25.3% coverage, while standard sensor-based systems would only achieve 4.4% coverage area in the same experiment. In conclusion, we proposed a Wi-Fi sensing-based soil sensing system, which leverages Wi-Fi signal propagation within the soil to identify soil properties such as moisture sensing, texture sensing, and position identification. Thank you for taking the time to listen. If you have any questions, please feel free to email me. Thank you, everyone.